Good afternoon and welcome to the next session. My name's Kerry Allen. I'm the General Manager of Hancock Forest Management New Zealand and also Director of Forest Growth Research. This afternoon the next topic, and we've got three speakers with four slots or four papers, and it's on digital and automated forestry. Obviously critical to our future and has served us well even to this point, but the whole automation and digital world we're in today is so important as we move forward with our forestry operations. So I'm really pleased to introduce three speakers, as I said. The first is Thomas Paul from Scion, and Thomas will be talking about scaling up and wilding conifer detection at a mega landscape level. So really looking forward to that, Thomas. The next two papers will be presented by Keith Raymond from FGR, who many of you will know. The first one around automated yarder and grapples, and the second one around winch assist harvesting. So that has been a real big area of focus and development in New Zealand, and it's progressing even further. So really looking forward to those papers too, Keith. And the last paper today will be presented by Karen Bain from Scion as well, and it will be around new value chains through automation. So really we know around the whole disruptive period we've been with COVID and value chains and how we can maximise efficiency. So that's going to be a great paper to look forward to as well. At the end of those presentations, we'll have a Q&A session, as typically we have with all the other presentations as we've gone through them. And I'll chair that, and you'll be able to provide and ask questions, and we'll ask our presenters to talk to those and answer as appropriate. So really looking forward to a great session, and thanks for attending the FGR conference via webinar. Pity we're not all together, but maybe this time next year. So enjoy the afternoon, and we'll talk later. Thank you.
Hi, my name is Thomas Paul. I work for Scion Research. I'm a forest ecologist, and I will talk about parts of our Winning Against Wildings program, looking at remote sensing and detecting wilding conifers in large landscapes. All right, mapping trees across large landscapes is a specific challenge, especially if at the same time the capture of details about the detected trees is required. Today I want to talk about a number of projects that Scion conducted in collaboration with the National Wilding Conifer Control Program run by MPI and the government, which all lead to developing remote sensing approaches to detect wilding conifers across large landscapes. But first, a bit of background. Why do we actually have wilding conifers in New Zealand? And I will use the mountainland revegetation research as an example. In the 1960s to 70s, several hundred different plant species were planted at altitudes from 800 to 1500 meters because New Zealand feared that their mountainlands are eroding at an incredible speed and something needed to be done. However, many species, including most natives, failed completely when they were planted in those areas, but not so exotic pines. With that, the Forest Service and the high country land managers planted most successful species like lodgepole pine, Scots pine, ponderosa pines in those mountain lands as woodlots, erosion protection and shelter belts. But those wilding conifer, but those pines are now our most prolific wilding conifers. In 2014, this was realized that we're getting an increasing problem of wilding conifers in our high country, and the government developed the New Zealand Wilding Conifer Strategy. And this was done because we wanted to eradicate or contain existing infestations and prevent further spread, as historic data showed that the extent of wildings will exponentially grow over time, as this one graph on the right-hand side shows. At the same time, researchers started to develop a research program to support that strategy and providing research into impacts, legacies, detection, which I talk about today, control and prevention measures to stop this. In the detection space, the vision was to be able to map and support the management of infestations at various scales in the landscape, as it is essential to be successful, that you have to know where and at what stage wilding conifer infestations are, and this becomes instrumental to manage and control wilding conifers. So with this in mind, we look to develop a scalable approach from landscape to individual trees to measure and map them in New Zealand from the landscape down to the individual. To be able to do that on the landscape is important for management operations to understand how big the problem actually is. The area of incursions, we wanted to understand how quickly those infestations actually spread, and to be able to detect them early enough to be efficient in our management. On the individual level, we aim to record metrics of those trees that help us to optimize our management and our control operations. With that kind of approach identified, we realized that probably remotely sensed imagery from a number of platforms are the better candidates. So from manned aircraft or from UAVs, capturing high resolution and spectral composition imagery would serve probably that purpose. However, there are a few challenges if you try to do something like that. For example, the capture of that kind of data need to be efficient and economic, especially if you deal with 2 million hectares around in the high country, which this map shows in green. Furthermore, there's a high diversity of landscapes and vegetation cover types that you have to deal with which makes detection algorithms complex or difficult to deal with. Also, the detection of small trees or outliers is a critical step, and that is shown in the lower photograph below, where I circled small trees that are already there, which are already hard to see, even if you just look over the landscape. Those kind of situations can really develop fast from those scattered outliers into dense stands, where the effect of the infestations are detrimental and often irreversible. So really, control needs to happen before invasions can spread further, so the trees growing too big and start coning already. So as a first task, we worked on a paper to really identify the detectable size with imagery that is readily available and can be captured over large areas. And we compared a range of platforms, as said, UAVs and manned aircraft, and various sensors, including LiDAR and spectral. The study identified that we are really comfortable and we have a good accuracy to detect wilding conifers that are of a height of 1 meter or above. That's actually a critical height in terms of development of a tree, as in the high country we found that one of our most sporadic spreaders, lodgepole pine, would start coning if it reaches that size or over, and we wanted to be able to detect infestations before this occurs. So really most practical for mapping was the use of multispectral imagery captured by manned aircraft across large areas, and then using that with models or algorithms that often work on supervised pixel-based classification. While this gave us confidence in the mapping side, we wanted to test the usability of exactly those combinations to derive certain metrics from those remote sensing maps to look at how can they actually support the management of wilding infestations. And we used the basis of that as a paper that has recently come out that we worked on to look at how complex and how the costs are actually driven when we deal with wilding infestations and want to control them. So there were really 3 metrics that stood out, and they came out in that flowchart that you see on the right-hand side, and mainly in the green boxes. And that's identifying really and understand the real area that needs to be controlled. So where are those trees and how are they looking? The density and the tree size that comes with it. And that's critical for applying the right control methods that can reach from boom spraying to individual cuttings. And the big question afterwards was really, is there a follow-up required, or are we successful with just one hit in terms of control? So with this in mind again, we embarked on the acquisition of 2 imagery types for 2 areas in Molesworth. Molesworth sits in the northern part of the South Island, is currently probably the biggest management unit that the Wilding Conifer Control Program is managing at the moment, and conduct large control operations. As said, 2 approaches were used, imagery was captured, RGB based or multispectral based, and then we applied 2 different approaches linked to the imagery that we captured. One was a geo-artificial intelligence tool, a convolutional neural network, and we used the RGB for that with a very fine resolution of 8 centimeters. We conducted another approach, which was a simple feature collection and extraction system or algorithm, which is kind of a semi-automated model. And we used the multispectral imagery, which had a lower resolution of 25 centimeters. So while the study is still ongoing, I will just present the brief results utilizing the multispectral imagery, because that gave us really good results. So we really captured the whole area of 176 square kilometers using the multispectral imagery. We ran our semi-automated classification approach, and what you can see on the map in dark red are actually the infestations in that landscape. Now we're getting a good idea about how far the infestations have spread in that area and where they're located. Here especially around the homestead and close to woodlots and shelter belts, which is shown in red. In total, nearly 2.5 million square meters of this area is covered in live wildings. In other terms, you could say 242 hectares out of the 176 kilometers has really canopy cover of wilding conifers. So that's roughly 1.3% of the total area surveyed, and that indicates a little bit how complicated it can become when you try to operationally control it, because you need really to know where they are and at what density to be able to do and conduct targeted control. So it's like a needle in a haystack, especially if we look at the size distribution that I show in this slide. So this is really a histogram about canopy sizes of individual or clustered wilding conifers across Tarndale. And it shows that when we calculated canopy area, that a lot of really small trees are in that landscape. Small defined here as a canopy cover of 3 square meters of canopy cover individual trees. And those really make the bulk of the scattered trees. On the other side, we have areas where trees are really densely clustered with over 20 square meters in area, which is shown on the right-hand side of that graph. So this is important because that already highlights the need for a range of control approaches, which mainly work on density and size classes. So what you can do with that kind of captured and modeled data is then use that demographic data that we're getting out of it and the density to allow the calculation of hotspots. So really dense areas with larger trees that allow, for example, boom spraying, which is one of our most cost-efficient control operations that we have available. And those are shown in that map as a more detailed one in the pink areas, while the blue ones are really the scattered individual tree crowns of single trees, which probably will require work on the ground like cutting or spraying individual trees. Another important aspect of that is, and it shows in the map in the red circles, is that there have been already control operations in that area, which are the dark red areas, which indicates dead trees. But it also shows that a lot of individual single trees are still in there that haven't been really affected by these control operations, showing that there is a follow-up required in those areas if you want to eradicate wilding conifers. So really the outcomes, how far we got, is that we're now getting to a stage, I think, where the wilding conifer management and the operational control operations will start using large-scale remote sensing and the associated mapping approaches to map wilding infestations across the wide landscapes and use the data, the detailed data that comes out of it for control operations and for planning to get the efficiency gains that they really need. Time series will allow the monitoring of control operations if we do that on a regular basis, and we can identify the efficiency, as well as new models based on remote sensing technology will contribute to the better prediction and invasion modeling. And I will quickly like to thank all the science team.
Hi, I'm Keith Raymond, Harvesting and Logistics Program Manager at Forest Growers Research. This presentation showcases some new technology innovation for New Zealand harvesting operations. This is the first successful project to come out of the Primary Growth Partnership in Forestry, Automation and Robotics, which is managed by Forest Growers Research and co-funded by the Ministry for Primary Industries, the Forest Growers Levy Trust, forestry companies and manufacturing partners in New Zealand. The Automation and Robotics program is based on a proposed new harvest process on the landing and new automated log sorting facilities off landing. The vision for the automated forestry value chain is no boots on the ground, no hands on the log. One of the first projects off the blocks was to develop a semi-autonomous hauler control system and smart yarder grapple as seen on the bottom right of this concept diagram. We collaborated with Rosewarne and May Limited, an engineering company based in Whangarei, as our manufacturing partner in this project. As we all know, grapple yarding using hydraulic grapple carriages is highly productive, and it's a lot safer to operate than using manual breaker outs. So one of the program's objectives is to increase the use of grapples. This objective aligned closely with Rosewarne and May's goals in developing a semi-automated hauler and grapple carriage. So a little bit of background about Rosewarne and May. They are the design and manufacturing division of the Rosewarne group of companies that's based up in the Northland region. They developed the ROB, or Remote Operated Bulldozer Winch Assist System, back in about 2014. The directors are Ian May, the engineering side of the business, and Lars Rosewarne, a well-known character in the New Zealand logging industry. The other company that's involved is Rosewarne Cable Loggers, which is a large harvesting contractor in Northland, contracting to Hancock Forest Management and Raioniea Matariki Forests. So what was the project about? From Rosewarne and May's perspective, the drivers were really to resolve a lot of the issues that are associated with existing hydraulic grapple carriages and to deliver efficiencies for their tower yarder operations, to achieve wider uptake of grapple carriages, to increase the utilisation of those existing systems, to improve health and safety, removing manual breaker outs from the risk. And from an automation point of view, one of the drivers was really to try and reduce the workload on hauler operators so that they have a bit more job satisfaction. So the objectives were to design, manufacture and commercialise a semi-automated tower yarder with an integrated grapple carriage. The Thunderbird TTY-70 tracked tower hauler was the base machine for the prototype, and it was designed to have features such as hydraulic skyline control, controlling the skyline tension and ground clearance, and reducing wear on the skyline, sensors for collision avoidance during normal operating conditions, a new type of grapple to use a swinging arm rather than direct connection of the grapple to the carriage to reduce shock loading, and a new hauler cab for improved operator comfort. The system also enabled retrofitting the automation to other yarders with no opportunity cost of lost production during the refit through using this first prototype as a swap machine for the next client while their machine was being retrofitted. As the concept design was already undertaken by Rosewarne and May, the IP sits with them. Large elements of the ROB technology were used in terms of the winch control and radio remote control. Field testing would be undertaken locally with Rosewarne cable loggers, and manufacturing meets ISO standards. So looking at the grapple design, there's a number of key features. Rosewarne and May wanted it to be a simpler design with a swinging arm to reduce damage to the carriage. They wanted to use off-the-shelf components as much as possible, and they wanted it to be light but strong enough to handle the robust nature of the work. So looking at the development of the project, in September 2018, Rosewarne and May put together a proposal to forestry companies Hancock Forest Management and Rainier Matariki Forests. The forestry companies saw an opportunity for an industry-wide project involving forest growers research with funding available from both the Forest Growers Levy and MPI. The first project meeting was held in November 2018, and investment was agreed between the co-investors in the project. The design commenced in January, and the second-hand base machine was purchased in September 2019. It was originally planned that the construction would take about 12 months, but COVID-19 shut down in 2020, and the effect on international supply chains in terms of delivery of hydraulic components from overseas has delayed progress. The project funding. The contribution of the partners is roughly 20% each, for Rosewarne and May as in-kind contribution, the two forestry companies together and FGR making up the industry funding of 60%. The balance of the project budget, 40%, is MPI cash. The total budget was $1.3 million that comprised design and build of the alpha prototype for $1.125 million, and in year 2, there was a budget for an additional $179,000 for field trials, industry demo, and commercialization. The total cost of the build ended up at over $1.5 million, the additional expenditure being funded as in-kind contribution from Rosewarne and May. Looking at the work plan, there were 3 development stages. Stage 1 was preliminary work made up of purchase of the hauler components and spare parts, engineering design drawings of the grapple carriage, and stripping down and refurbishing the hauler. The second stage involved building the hauler cab and the fabrication of the grapple, installing air, electronics, and new winch gear. Stage 3 involved setup and field testing, which is the stage that we're at now. Firstly, the hauler was stripped down to the tracks, motor, and transmission. Hydraulics, pneumatics, and winches were taken out, and the main and tail winches were refurbished. The most work that was done was to change the skyline winch, which was the key part of the whole project, pulling the skyline drum out, chopping the original shaft, milling spline hubs on each end of the shaft, and fitting 2 new hydraulic skyline motors. Then the hydraulics were replaced with new hydraulic controls for the valves, and a new air control system was fitted. For the hauler cab, they basically built a new cab altogether. and then a new electrical system was fitted, which was totally different. They installed a CAN bus system, which is common technology nowadays in industrial automation. The CAN bus, or Controller Area Network Protocol, is a communication system designed to allow microcomputers and devices to control different functions and communicate with each other without a host computer or complex wiring. One module controls all the engine management. One module controls all the hydraulics, one controls all the sensors, and one controls the air system. Each of these computers is communicating to each other all the time, and it's all done through only 2 wires communicating between the whole lot. Stage 3, the field testing. This commenced in December of 2020 at Rosewarne Cable Loggers. Trialling the hauler in a difficult setting in Pipiwai Forest, Whangarei, extracting stems over 500 metres away. So what were some of the learnings from the first trial? Firstly, the Skyline drum had plenty of power. That was important. But the Skyline drum speed appeared slow, so Rosewarne and May decided a change in gear ratios was required. There was very little line wrap between the Skyline and the mainline, which was originally foreseen to be a problem. And the hydraulic cooling, oil cooling, was not sufficient in their view, and some modification to the cooling system was required. From an operator perspective, the tension monitoring system displayed in the operator cab was working well. Excellent visual alerts, with the screen being able to be switched at the push of a button. The AgCam camera was working well, with a clear image and very little interference. And even though the operator had only been working the machine for 2 days when these trials were done, he was coming up to speed quickly. And he was impressed with the reduced workload due to the automation of the Skyline on in-haul. Looking at the grapple carriage, the original grapple tines seen on the top photograph were too large and appeared to be slow to open and close, so they will be modified. The power to the grapple arms and rotator function goes through the shaft of the hanging bracket, so there are no loose hoses to snag when the carriage is operated. Another factor on the grapple carriage was the installation of a sensor for collision avoidance. They found this was mounted too high on the carriage, and this will be relocated. The hydraulics in the carriage were also modified with a new valve bank installed. The major feature of the grapple and hauler control system is the semi-automated hydraulic Skyline control, raising and lowering the Skyline automatically to maximise deflection during in-haul and tracking the terrain. This is shown in this brief video clip of the in-haul. Here you can see the Skyline drum is initially winding in. Then it stops and starts to wind out to lower the Skyline, maximising the deflection. This is all done without the operator's control. The tension is maintained within safe working load of the Skyline at all times. And in-haul on the main line and out-haul via shotgunning or gravity return is controlled directly by the operator. So an update on the development since the initial trials. Rosewarne and May have further developed the software for hauler control. They've modified the hydraulics in the grapple carriage, changed the claws on the grapple, but these will be further modified. The Skyline control and tension monitoring system is working well, and Rosewarne and May hosted a field demonstration to project co-investors back in April of 2021. The Skyline drum ratios have not been changed yet. Looking at the next steps in the project. The next steps are to complete all planned modifications. These are expected to be completed later in 2021. Organise an industry-wide field demonstration once those modifications are complete. Integrate machine vision for stem recognition for the grapple carriage on outhaul is the next big step of the project. This is a view of machine vision of a stand of trees taken from a carriage as it moves back on outhaul in a European operation. FGR completed an RFP process for stem recognition for the grapple carriage in December of 2020, and this work is due to commence this quarter. In the future, implementing automatic lowering of the skyline and positioning of the grapple is foreseen. Automatic stop at the landing edge, lowering of the skyline and landing of the load, and automatic carriage return back to the breakout site. FGR also intends to conduct full production trials in 2022. So in conclusion, this project has been a collaboration between Forest Growers Research using the Forest Growers Commodity Levy Funds, Ministry for Primary Industries through the Primary Growth Partnership Fund, the forestry company stakeholders, Hancock Forest Management New Zealand Limited and Rayonier Matariki Forests, and Rosewarne May Limited, the manufacturing partner. Thank you. This presentation on winch-assisted harvesting showcases a significant technology innovation in New Zealand harvesting operations, coming out of the first primary growth partnership in steepland harvesting, managed by Future Forest Research, or FFR, the predecessor of Forest Growers Research, and co-funded by MPI and the forest industry, and supported by research at the University of Canterbury School of Forestry. The safety and productivity benefits of mechanical tree felling on easy country were well known, but the development of winch assist enabled these benefits to be gained in steep slope harvesting operations. This winch assist technology is now well established in New Zealand, but how did it come about? Since 2006, some new machines and systems were being developed by New Zealand contractors to mechanise felling and pre-bunching on slopes, with the aim of eliminating manual chainsaw felling and cable operations. In March 2009, FFR researchers visited Ross Wood's operation in Nelson with a view to studying his steep terrain bunching operation. This was initially an old Komatsu roller crusher tractor with a pre-tensioned winch drum brake. This system, designated A in the illustration on the left, is an active system as the rope is moving up and down the slope as it is wound in or out to assist the feller buncher. At about the same time, the second machine that had been developed back in 2009 was being tested by Nigel Kelly of Kelly Logging Limited in Nelson. This was a Hitachi excavator with a Satco boom and felling head with a built-in winch to aid traction. This was a single machine system, designated B in the illustration on the left. As it is a passive system, the winch rope is static as the machine moves up and down the slope, winding the cable in or out. This means less rope wear as it is not moving across the ground, and as the winch rope is tied off on stumps at the top of the hill, it does not require access to the back line or the top of the slope. So, at the risk of getting a bit technical, let's have a look at how a winch cable can be used to assist the traction capability of a ground-based machine on a steep slope. As shown on the figure on the left, the basic physics for retaining traction on a slope is that the gravity force pulling the machine downslope, WG in red, should not exceed the traction force, T in blue, that the machine is able to develop on the ground surface. Otherwise, the machine will start to slide down slope. Put simply, the greater the traction force the tracks can generate in the soil, the steeper a machine can operate without slipping. The benefit of winch assist is that the tension provided by the cable will add to the traction force of the tracks and thereby greatly increase the operating range of the machine without it reaching its traction limit. Traction force is a function of the soil's coefficient of traction, which is sometimes called tractive efficiency, for a given machine type, either tracked or wheeled. And this is illustrated in the chart on the right. The slope limit is indicated where the WG purple line intersects the traction line for a given coefficient of traction. In this example, if the soil had a coefficient of traction of 0.4, the blue line, a 37-ton machine would start to slip on a 22-degree slope without traction assistance. By adding a winch assist with 10 ton of tension provided by the cable, C, represented by the black arrows, the traction force is augmented by the cable force, which extends the operating limit of this machine to about 37 degrees, a major improvement in operating range on steep slopes. But winch-assisted harvesting is not new, with this machinery commercially available in forest operations in Europe since the 1990s. A number of different companies were offering cable assist products, initially on forwarders and later on harvesters, to expand ground-based harvesting onto steeper terrain. The separate winch units were mounted to the rear of the machine, as shown bottom right of this illustration, and more recently for skidders, top right. In Europe, independent self-powered winch units were also being developed, as shown in the bottom left. However, New Zealand conditions include very steep slopes and unstable soils, in combination with large tree size, which has required larger felling machines with larger winches and bigger diameter wire ropes than were commercially available in Europe. So in New Zealand, the tracked excavator winch assist systems were developed, as illustrated in the top left. Let's have a closer look at the range of winch assist machinery. In Europe, the most common approach was to mount the winch onto the chassis of the primary machine. A number of manufacturers preferred the bolt-on option to provide the opportunity to remove the unit when not required. This EcoForce T-winch is one of the first independent self-powered remote winch units, which was developed in about 2012. In New Zealand, the first commercial winch-assisted harvester was the Climax steep slope harvester developed by Trinder Engineering of Nelson with funding assistance from the Steepland Harvesting PGP. It had an integrated winch mounted into the track frame of a Hitachi excavator with a Trinder boom and felling head. Shortly afterwards, Electrical and Machinery Services, or EMS, in Rotorua produced a dual winch system on an excavator base, which they called the traction line. This has been a very successful development. Shortly afterwards, Rose Warner May Limited in Whangarei produced the Remote Operated Bulldozer, or ROB, winch assist, which is a dual winch mounted on a hydrostatic drive John Deere tractor. And DC Equipment Limited of Richmond Nelson produced the Falcon winch assist, a single drum winch on an excavator base. And in the US, Summit Attachments and Machinery Limited in Washington State produced a single drum winch on an excavator that had a boom extension. And in British Columbia, Canada, Timar Industries produced the LogChamp remote winch assist, an independent self-powered winch unit similar to the EcoForce T-winch. So looking at some data from the FGR benchmarking database run by Dr. Reen Visser at the School of Forestry, from 2013, the database started to record operations on steep slopes using winch assist. This early analysis in 2014 of only 13 mechanised felling operations compared to manual felling showed operations on steeper slopes with higher productivity and lower costs than manual felling. A survey in 2016 found that over 90 winch assist machines had been manufactured in New Zealand. There are now 4 main New Zealand companies manufacturing winch assist machinery: Climax Equipment Limited, EMS, DC Equipment, and Rosewarne May. Together, they have reportedly manufactured more than 270 winch assist machines since the first commercial machine appeared in 2012. The Benchmarking Harvesting Cost and Productivity project has been running now for about 12 years, and the data tells us that around 65% of cable harvesting operations in New Zealand now have access to winch assist machines. That's about 200 machines across the whole of the New Zealand logging industry. With regard to safety, consideration of the actual tensions in the winch rope becomes critical. If the machine is not stable on the terrain without the cable. From 2014, work at University of Canterbury School of Forestry by Hunter Harrell looked at winch rope tensions. From these studies, it was found that average tensions during felling and shoveling were usually below the safe working load of the winch rope. But tensions during machine movement often exceeded safe working load. In this example, was 14.2 tonnes. For very short periods, which are the blue spikes seen on the chart, and during the moving phase only. From 2016, the School of Forestry has been running workshops on winch-assisted harvesting, using information from FGR harvesting projects and the benchmarking database, to undertake operational planning of productivity and cost, supporting contractors and operators in the safe use of winch assist, and to determine areas for further research and development. Some of the things that the workshops have been looking at: operating techniques. In New Zealand, most operators use trees or stumps to change the rope angle to facilitate better machine utilisation. When the feller buncher gets to the top of the ridge, they go around the next stump and back down the hill to avoid shifting the winch machine on every pass. Some manufacturers' guidelines specifically allow for the use of these hold stumps. However, there have been issues with the winch rope pulling over trees or cutting through the stump, causing hold stump failure. Another issue on the subject of safe use of winch assist machinery, the workshops looked at areas such as the connectors between the winch rope and the felling machine. Which ones are best and how to inspect and maintain them. So coming up to date, there are a number of recent or planned studies to be undertaken by the University of Canterbury School of Forestry of different applications with skidders, forwarders and harvesters. They include a skidder extraction study using a Falcon winch assist at Spears Logging Limited's operation in Gisborne. The winch assist gave the skidder the ability to extract away from the riparian zone, hauling loaded uphill. The skidder was operating on slopes up to 33 degrees with an average of 25 degrees adverse. Utilisation of the winch assist was increased when used by the skidder, up to 80% utilisation, compared to just the falling machine, which was 50% utilisation. In another study of a cut-to-length harvester forwarder operation near Napier with Rainier Matariki Forests in April this year, a John Deere 1910 forwarder was operated supported by a T-winch Model 10.2 winch assist. In the same operation, the harvester was using a traction line winch assist for cut-to-length processing at the stump. Delimbing on the slopes, which was first mooted back in 2013 in an earlier FFR study, is now a reality with the use of winch assist. Stumps are used to hold the logs in place on the slope, and designated slash tracks are set up for the forwarder using processor slash to reduce ground disturbance. So in closing, there have been numerous studies of winch-assisted harvesting operations published over the last 10 years. Some of the FFR and FGR studies are listed here. Winch-assist harvesting systems have seen rapid adoption and implementation in Europe, New Zealand, and North America during the last 10 years, and continue to do so in other parts of the world. This technology is considered to be one of the major innovations in steep terrain harvesting in the 21st century. There will continue to be more research undertaken looking at machine stability, safe operation, environmental impacts, and system productivity and costs. Not only comparisons between winch assist and conventional systems, but also between different winch assist systems themselves. We expect the substantial body of literature will continue to grow. The FGR project has been a collaboration between Forest Growers Research, supported by the Forest Growers Commodity Levy, and MPI through the PGP, and forestry company stakeholders, and the University of Canterbury, notably Dr. Reen Visser at the School of Forestry, and of course New Zealand manufacturing partners. The focus on mechanisation and modernisation of steep terrain harvesting systems across the industry over the last decade has shown significant improvements in both productivity and safety. A major step change has been the development of winch assist technology. Winch assist has proven to be a robust, safe and high-performance forest harvesting technology that has significantly increased the operating range of ground-based mechanised harvesting on steep slopes. Thank you.
Hello, good afternoon. My name's Karen Bain. I'm a senior scientist here at Scion, and I'm also the project leader of the value chain optimisation team at Scion. My topic today is about new value chains in automation. New value chains through automation is part of the Forestry Work in the Modern Age Primary Growth Partnership, and I'm presenting this on behalf of my colleagues and Keith Raymond. So digitisation is disrupting the forestry supply chain. So in the past, supply chains traditionally focus on the flow of goods through the supply chain, but now information is becoming more important, and the flow of information between stages within supply chains and from suppliers right through to the end of the chain is becoming more important as well. And this is being caused and driven by real-time big data and analytics, and also through the fact that we've got much more connected devices and the Internet of Things is out there, so there's a lot more information around. Automation itself is also producing a lot of information and data. So things like drones and self-driving vehicles, mechanisation, semi-automation and remote control systems, sensor technologies and GPS and positioning systems, all creating data that can be used and information that can flow through the supply chain. So the introduction of automation within the supply chain is also adding these further information sources. Another large driver within supply chain management is how to handle increased circularity in supply chains. So industries are looking towards the circular bioeconomy, and this can add quite a lot of complexity. So just an example from of a beer supplier. So if we look at Heineken's traditional supply chain, it's focusing on efficiency gains and incremental value improvements within each stage of the supply chain. This is in quite a linear fashion, and so Heineken's supply chain, they say it goes from barley to bar. If we compare this kind of a supply chain with a small boutique brewer, the Wildwood Brewing Company, you can see that it's incorporating a much more circular approach and a lot more information flowing through that supply chain and a lot more complexity into the system itself. We can see this also within the forestry supply chains. Automation and digitisation is occurring at all stages. So at the planting stage, we've got things like drone delivery and mechanised planter heads going on there. We've got automated log loading occurring, and at the port we've got these robotic log scalers adding information flows. And further down the supply chain and the processing side, sawmill digitisation systems, and also through into house and construction industries with robot prefabrication, so using robots to make prefabricated framing and robotic erection and construction of that. So one of the things that we are looking at Scion is how to understand simulation modelling of supply chains. So why simulation modelling? Well, companies are really excited by automation and the potential for automation looks really good, but they're thinking, well, how would this impact on our supply chain if we adopted into this technology? How do we get to see how the technology will impact on our supply chain? And are we able to quantify those benefits that people are talking about in some way? So what simulation modelling allows for is the ability to give a digital twin. You can build parameters of automation into your production system through the digital model, see what the impacts are and quantify those benefits over time. It provides outcomes over a time series and allows for some sort of seasonality. So it's a dynamic modelling system. You can also integrate the supply chain segments across business interests, integrating stocks, piles and resource equipment, people and facilities. So it identifies those sorts of what-if scenarios. Where are the likely impacts and can you look at what's happening upstream or downstream and the disruptions in there. So you can manipulate the supply chain system without physically altering anything and building anything on the ground, look at future options compared to a current operating system. So it provides agile decision making, the ability to foresee and react to potential impacts much earlier on in the production system and cycle. So you can also tweak the model, add in some scenarios, see what happens if there is disruption. So what happens if there's disruption in your supply chain in general, but what happens if the technology is implemented within it. And also what might happen if you introduced a more integrated or circular supply chain management into your business system, or if your suppliers or customers do as well, what the impact is on your business. So some of the components that we might look for in simulation modelling, at the harvesting stage, from the forest to the sort yard, you could have a look at scenarios like increasing or decreasing the cut rate and the impacts of mechanising and automating some of the processes, or introducing a central processing yard. At the sawmill or the pulp mill, you could look at production seasonality with pulse or breakdowns, and look at export demand or demand increase or reduction. At the port, we could look at things like pre-port scaling, so taking the scaling away, use of off-peak trains, and things like smoothing the truck dispatch or the addition of another berth, or if one of the berths is out of action. The other aspect of simulation modelling is that you can not only look at supply chains within your own company, but look at how the whole value chain is interactive. So the changes in one part of your supply chain, looking upstream or downstream. So I want to give you an indication of what we've been doing in the PGP program in harvesting with regard to this simulation modelling. So a key aspect is to introduce some automation at the landing through new automated equipment, but also to introduce automation to assist in sorting and transportation timeframes. So our current harvest process is got things like steep slope felling and bunching, quite a lot of log stacks on the landing, extractors and excavators, and quite slow loading onto a truck. It's supposed that we might go to a new harvesting process that might introduce things like a debarker processor at site and a central sort yard, And you might be able to have a semi-autonomous hauler control systems and some residue management systems on the landing. Or the other aspect is to get the sort yard right off the landing area into a centralised log sorting facility using robotics. So using smart scanners, robotic log sorters, and introducing a automated gantry loading system for your trucks. So what would this mean in reality for some of the crews on the harvesting system? So in this we would go, for example, with a mechanised hauler. With the conventional mechanised hauler, you're using a winch assist feller and chainsaw, swing yarder, through into grapple processing and loading and onto a truck. With the automated hauler, the winch assist and feller is going to a winch assist feller buncher. We're semi-automating the yarder system, and the whole processing system is going to a processor debarker loader, and we're looking at residue management so that we've got an automated chipper on site that's taking residue away from the landing. We are reducing our personnel from the conventional from 9 people to 4 people. However, we are also introducing a log sort yard concept as well, which needs to be staffed with some personnel. And so in this we are looking at going to the log sorter, that includes the debarking, into some kind of either overhead log truck loading gantry or else into log storage system. So what we've done within the PGP program is to look at what the potential is for such a fully automated system in a forest environment in New Zealand. So looking at an 8-crew system, taking the conventional model, the same types of crews or crew types, and automating these. But with the introduction of this centralised log sort yard that's also fully automated. And we found in this that we would reduce our labour inputs from 64 workers with the conventional model to 53 workers with the automated model. But we really want to look at the buffers and stops and flows in the forest system. What impact is there on throughput and production? What's the economic benefits? What's the payback on the capital investment? And so going from that conventional baseline to an automated baseline using some kind of system and understanding how stock gets buffered through the system as well. One of the other aspects that we're looking at is to do with trucking. So we're looking at introducing off-road trucks and newer dedicated on-road trucks. And this has road design implications and subsequent cycle time implications also. So under a current system with 8 crews, each of those crews are taking logs from the landing directly to either a mill or the port or the pulp mill. However, using the introduction of this new log sort yard process, the automated crews would be going directly with no sorting on the landing to a sort yard, and then the sort yard would be taking the logs to pulp mill or port. There would be some residue management, so those little green dotted lines are the residue management system going direct to pulp mill. So one of the things we wanted to do is to just sense check some of this. We got some very good indications of potential out of looking at this automation system, but we need to sense check them. And given that the automated configurations aren't actually in existence, they're still yet to be built, we decided to sense check by running the results of the conventional processes through the School of Forestry benchmarking data. So this has got 1,600 unique entries over 12 years, and hoping to give some confidence that we can trust the simulated automated operations as well. So we were expecting that if our model was correct, then we would get similar numbers from our conventional system to the benchmarking data. So we can see that we have got quite similar results from our simulation to the benchmarking data set in terms of production figures. And this provides some confidence for the automated modelling is correct as well. Just note that the swing yarder with two-stage skidder, it's a little different there, and that's because the benchmarking data was on two-stage operations but wasn't able to differentiate whether it was a swing yarder or not that was used, as opposed to the others where it was much more aligned to our system that we were modelling. So when we looked at our 8-stage crews and the log fully automation and fully automated log sort yard, it included the centralised sort yard and different transportation configurations of off-road trucking. And the net present value was positive, a very short payback period, and reductions in operation costs through both trucking by getting the right trucks going on the right roads, and also in terms of just efficiencies as well, and increasing our system throughput per year significantly as well. So what's next? What's next is trying to customise the simulation model for specific harvesting value chains. So we've done a baseline indication. What we really want to do is look at some other aspects. So looking at the centralised sort yard and log identification introduction, looking at improvements to some parts of the value chain of the harvesting or the processing of logs through adoption of automation technologies, looking at dedicated off-road trucking and getting the right trucks on the right roads, maybe looking at that overhead gantry system. So we're working with 2 forest companies at the moment to model their value chains and their priorities. We're keen to work with others. Get in touch with us, myself or Keith Raymond, and we're planning to evaluate 3 or more options by 2026. So that's it from us, and looking forward to hearing your questions at the end of the session. Thank you very much.